Hello, welcome to Group 14 Senior Design Project, the Motor Assisted Cooler, or MAC. Alright, let's meet the members of the MAC team. It consists of two computer engineers, David Crumley and myself, Min Park, Akil Ahmed, and Fong T. Duong. The description for this project is to design and create a motor-assisted cooler which will enable the user to transport cold beverages and or food items to and from their vehicle with less strain on their body. The motivation for our project is to make sure our device can traverse all sorts of different terrains, such as sand, gravel, grass, and concrete, keep our cold storage items cold for longer, and have fun while doing it. To accomplish this task, we have set up our goals and objectives to four main parts: the motor-assisted cart for mobility, our Peltier cooling device to keep our cooler cold for longer, power distribution to manage our power consumption from the motors and cooling device, and finally our solar charging component to keep our cooler running for longer by increasing the battery life. Here's our specifications we are currently running. For our entire system we are running two 12-volt batteries in parallel, and to completely discharge them it would take 2 hours, while it would take 6 hours to charge them fully with our solar panel. The Peltier cooling unit takes up to 30 to 45 minutes to reach 40 degrees from room temperature for our cooler. The temperature controller can measure between -50 to 150 degrees Fahrenheit. Our solar panel produces 50 watts of power, and our motors generate a maximum of 480 RPMs. Here is the visual representation of the four major components alongside our task allocation. Akil and Fong are in charge of our power distribution and battery charging, while I was in charge of the refrigeration system, and David, who had the task of making our system mobile, who I will now pass it off to.
All right, thanks for the intro, Min. My name is David Crumley. My major is computer engineering, and I am responsible for making the motor-assisted cooler motor-assisted. So we'll get started with the next slide by showing the system block diagram and outlining the major components of the motor control system. The motor control system will involve a 5-step process to give the proper output signal to the motors. Every iteration of the routine starts with the ADC reading the voltage from the potentiometer. The ADC will then convert this analog signal into a 12-bit digital value. The transfer function then takes the ADC reading and converts it into the correct duty cycle value for the given input. The PWM signal is implemented as an output pins of the microcontroller, which are connected to input pins of the MOSFET gate driver. The gate driver then controls the switching of the H-bridge circuit, which are connected to the motors. The motor speed control is implemented within the chosen microcontroller. The output of the potentiometer, being between 0 and 5 volts, will dictate the duty cycle of the PWM signal. The motor speed was originally to be controlled using a PID control algorithm. However, during initial testing of the motor control system, we found that the PID control was unnecessary, only providing a very negligible effect while adding more complications than it was worth. We also found during testing that the weight of the cart and the construction of the handle mechanism provided the needed dampening and steady-state error mitigation. By using a simple average filtering technique, we can reduce the ADC output error greatly. Because the ADC uses a 12-bit value and the duty cycle uses a 10-bit value, we simply needed to shift the output of the average filtering loop by 2 bits to get our desired duty cycle. So the input measurements, the PID calculations, and the output PWM signal are all going to be taken care of using this PIC 18F14Q40 microcontroller. This microcontroller was chosen for its low cost and low power consumption. The average current draw shown in the table, as we can see, during the time that it's fully operational at 6 milliamps when everything is operating to the full capacity. From the output PWM signals and making all calculations, right? So this is around a quarter of the current draw of a comparable ESP32, which you can see on Arduino, while it's in sleep mode. This is one of the main reasons why we chose this microcontroller, because it's low powered and also provides all the functionality needed for this subsystem. So the main advantages of choosing this microcontroller over a more powerful one are the price and the power consumption. It's only $1.08 per microcontroller, right? So based off these metrics, we decided this would be the best microcontroller for this motor control system. It does everything we need, and it's very low power consumption and low cost. So next, we're going to talk about the circuit that will be controlled by this MCU. So what we have here is the actual MOSFET circuit that will be powering our motors, and it'll be controlled by the MCU. And the circuit is known as a full H bridge. The four MOSFET transistors that we can see here are going to allow for the current to flow in both directions based on which MOSFETs turn on and off. This is going to give our project the ability to move in forward and reverse. So the major components of this circuit are the H-bridge gate driver, the MC33883, and the MOSFET transistors themselves. Every other component that we see here is for protection and current maintenance. For our H-bridge circuit, we have decided to go with the IRF Z44NPB. This component was chosen because of its low internal resistance of only 17.5 milliamps. This is a characteristic of the HEXPET power MOSFET category of which it belongs. This low resistance is important because it means that we can have 10 amps going through this transistor with there being only 1.75 millivolts across the transistor. This meaning more power to the motor. In order to turn our MOSFETs on and off at the right time and in the right way, we've decided to go with the MC3883 H-bridge driver. Because this IC is a full bridge driver, it takes 4 inputs and has 4 outputs, which go to each of the MOSFET transistors. The advantage of the full bridge driver over the half bridge is that it provides protection to the circuit by assuring that the wrong transistors aren't on at the same time. This can cause shoot-through and short-circuiting of the battery if not protected. This particular driver supports up to 100 kilohertz frequency, which is more than enough for this particular component. So the last component decision that was made for the motor control subsystem was the actual motors themselves. To power this cooler, the motor that was chosen was the Lynx Motion 12-volt motor shown here. This motor is the best 12-volt high torque motor that we can find, which also has an encoder and gearbox built into the case. Having this gearing means that the motor can provide more torque at a lower current draw and maybe a higher voltage motor without the gearbox. The motors will provide us with over 300 ounce-inches of torque at a max RPM of 480. While the RPMs are lower than without, and if it didn't have the gearbox, this is actually beneficial to our project because we're not looking for high speed, but high torque. All right, so now that I've talked about each main component of the motor control system individually, let's look at the final schematic of the entire system. So there is included a safety feature which was not previously mentioned. This is the user presence switch, which will be implemented as a trigger on the handle of the cooler. This safety switch will ensure that the system will never run without a user in control. There will also be some external programming pins for the tuning of the PID gains, as mentioned earlier, also for the inevitable debugging that will occur.
Here we see the PCB design for the motor control circuit. We used wider traces for the route which the current will flow to the motors. A 5-volt switching regulator is also integrated into the PCB to power the microcontroller and provide voltage for the potentiometer. Programming pins were also implemented for debugging and necessary program changes.
So before the complete circuit design and PCB layout was finalized, we wanted to make sure that the circuit actually worked. So we decided to test it on a breadboard. And we can see here in this picture the full circuit from before implemented on this breadboard. For the power supply, we used the power supply provided in the senior design lab with two channels, one at 12 volt and one at 5 volt. What we can't see in this picture is the potentiometer connected to the inputs of the MCU. And what we found is that the circuit works. In the next couple slides, I'll show the output showing positive polarity and negative polarity on the oscilloscope. So let's go to that. So we can see here the output waveform with a 50% duty cycle. Now this result was when the potentiometer was at the first quarter of its full swing. We can see that we have a nice 50% duty cycle constant pulse width modulation output. We can also see that the output isn't exactly 12 volts. This is actually due to our gate driver being damaged during soldering. After some other testing, we realized that it wasn't providing enough voltage to completely turn on the high side MOSFETs. They were only getting about 3 volts, while the lower sides were getting the full 10 volts. We believe that with some new parts ordered, this won't be a problem.
When the new gate drivers arrived, we replaced the old one in the circuit and did another test to make sure that the issue was resolved. We can see that when the gate driver was replaced, the output did indeed reach our desired 12 volt peak to peak. Here we can see the motor control layout and custom handle design. The handle is replaced with a two-part telescopic handle mechanism with spring dampening. The circuit is enclosed within a box attached to the base of the handle. Motors are attached using custom motor mounts to the wheelbase, and the output is connected to the wheels using a belt drive system. Attached to the lower end of the telescopic handle is the potentiometer, also enclosed. The sliding portion of the potentiometer is attached with a connecting rod to the upper portion of the handle in order to read the force being applied by the user.
All right, thank you, David. And now on to the refrigeration. There are four main types of refrigeration: mechanical compression, absorption, evaporative, and thermoelectric. The first three methods all require heavy components which are not great for mobility, so there was really only one option available to us for our project. The refrigeration method we chose for our project was by using a thermoelectric Peltier device. This particular method of cooling doesn't require any moving parts such as your normal house refrigerator or air conditioning unit, which uses liquids to move back and forth through the system. The Peltier instead uses an electric current to cool a targeted area. As you can see from the middle image, this device consists of an equal amount of N-type semiconductors and P-type semiconductors, which are placed in series with each other throughout the device, which is then covered by two ceramic tiles. On one side of the tile, it absorbs the heat, and with the absence of heat, we are left with the cold, which is where we get our cooling side. The other side rejects heat, which is coming from the cold side, making it very hot. While testing this device, it brought up two problems that we encountered. The hot side of the Peltier device was getting too hot, which could cause the device from burning out, while the cold side of the device wasn't transferring any of the cold into our cooler. To solve the hot side problem, we added a big heat sink and attached a fan to disperse the heat evenly in a safer fashion, and used the same solution for the cold side of the Peltier, using a smaller fan to create an airflow into our cooler. The image to the left is the final refrigeration device that we will be using for our system. All three items require 12 volts from our batteries. The Peltier device can take up to 10 amps of current, but during testing it only drew 4.5 amperes. The smaller fan, which is attached to another heat sink, draws 0.9 amps, while the bigger fan takes up to 0.2 amps, which is attached to the hot side with the bigger heat sink. During testing, our Peltier refrigeration device was able to get down to 40 degrees Fahrenheit in an hour with no items within the cooler. But when we added a plastic cup with ice in it, it took half that time. Because our design was using a cooler for its exterior, we concluded that our device didn't have to be on the entire time if our cooler was in use, thus draining our battery. To that end, we used a small thermostat with a relay with an attached sensor to measure the internal temperature of our cooler. This device draws 65 milliamperes of current and requires 12 volts from our source. We set the relay to shut off once the temperature reached 40 degrees inside the cooler every time without fail. We then set the temperature ceiling to 42 degrees to turn our refrigeration unit back on until it reached that 40-degree mark. These are the final items used during our testing of our cooling system, which consists of the Peltier refrigeration device, a 12-quart cooler made from styrofoam, and a temperature control unit to which the former and latter is ready to be used in our final design. During the assembly process of combining our three subsystems, we found an old cooler with a built-in thermoelectric cooler in our group member's garage. Much like our design, this one also had 2 heat sinks and 2 fans, so instead of cutting into a cooler and damaging the structural integrity, we elected to use this one instead for our final design.
Thank you. And now I'm going to explain the power storage of our system. Here we have the block diagram of our solar charging circuit. We are measuring current and voltages at the battery side as well as at the solar side and display it on LCD. The main part of this circuit is buck converter. We control its turning on and turning off timing using microcontroller. In original design, we decided to use 100-watt solar panel, but due to space limitation, we reduced the size from 100 watt to 50 watt. And during testing, we observed that our solar panel was able to give us a voltage between 17 to 20 volt. We are using two 12 volt 9 ampere hour lead acid batteries. Solar charger is charging these batteries and load is directly connected to them. Since the battery have these different charging stages, we make sure in our design that it should display those charging stages on LCD. And to avoid battery fully discharged, we display a message on LCD when battery is below the threshold point. Here we have the complete diagram of our solar charger circuit. It includes buck converter, voltage and current sensors, switching circuit, 5 volt voltage regulator to provide power to our microcontroller and different sensors. The microcontroller reads voltage and current values coming out of solar panel and calculates the power. Based on power, it makes a decision and generates a PWM of different duty cycle. This PWM basically turns on or off the MOSFET using the MOSFET driving circuit, and turning on and off MOSFET basically connecting or disconnecting a solar panel from the buck converter. We wanted to build a solar charger based on maximum power point tracking, so we can get the maximum power out of solar and charge our battery in less time. There are different methods available to get the maximum power from solar panel, and most of them requires information of hardware components. Since perturb and observe is one of the easiest and simple way to build the maximum power point tracking, so we implemented in our design. At initial, microcontroller reads voltage and current from coming out of solar panel and reads the power. If power is greater than the previous power, then we check the duty cycle. What was the duty cycle? If duty cycle is also greater than the previous duty cycle, we increase the duty cycle and go back again in the loop. And if duty cycle is less, we reduce the duty cycle. But if our current power is less than the previous power, then we can check the duty cycle. If duty cycle is greater than the previous one, we reduce the duty cycle. But if duty cycle is not greater than the previous one, we increase the duty cycle. And this loop continuously run in microcontroller and find out the maximum power. The left side is the first PCB that we designed for our circuit, but when we checked on a hardware, we realized the traces are too narrow and we actually burned our PCB. Then we designed another PCB with wide traces and make sure our PCB is capable of taking care of current up to 5 ampere. And this PCB is working perfectly fine, and it is the actual PCB in our hardware design. Here are some main components of our solar charging circuit. Since the circuit is taking care of high current, so we make sure the components that we are selecting should be able to handle high current, voltage, as well as frequency. We used 20x4 LCD to display our voltage and current values. We used Atmega 328P as a microcontroller in our design, and we programmed this microcontroller through Arduino. We used IRF-Z44N MOSFET. The reason we chose those MOSFET because they can handle high frequency, voltage, and current. To measure the voltage, we are just using series resistor and read voltage from them. We used ACS712 5 ampere current sensor. The reason we chose them, they are cheap, easy to calibrate, and we can display current with less error. We used 50 microhenry inductor in our buck converter design, and this inductor can carry a current up to 10 ampere. For MOSFET driving, we used a driving IC IR2104. We are also using some diode in our circuit, and the diode that we chose are 15SQ045 because they can carry current up to 10 or more than 10. Here are some pictures that we got while we were implementing our design and tested it. If we take a closer look at the right side of two pictures, it displays voltage coming out of solar panel and current, battery voltage and current, power of both things, and also the duty cycle. It also displays what is the current charging stage of the battery, and in case the battery is low, it displays the battery low message on LCD.
So the voltage regulator that we'll be using in our project will be a step-down switching regulator LM2576 adjustable version. This regulator offers a wide range of input voltage up to 40 volts and is able to try a 3 amp load with excellent light and load regulation. This regulator was designed to minimize the number of external components to simplify the power supply design. Since it is a switch-mode power supply, its efficiency is significantly higher in comparison with popular three-terminal linear regulator, especially with higher input voltage. This regulator has an external shutdown as well as the thermal shutdown for full protection under fault conditions. In our project, we will need one to step down the 12 volts from the battery to 5 volts for the motor controlling board and the sensor. We need another one to also step down the 12 volts to 5 volts for the microcontroller and the LCD display of the charger. Below is the schematic of our voltage regulator. The input voltage will be 12 volts and the output will be 5 volts. We also include the formula to calculate the resistor values for R2 and R1. We choose R2 being 3 kΩ and R1 being 1 kΩ to produce the output voltage of 5 volts. We performed the circuit testing in the senior design lab. We use the through-hole components because it's easier to plug them into the breadboard. We inputted 12 volts from the DC power supply to the circuit and successfully received 4.99 volts, which is 5 volts from the multimeter. The photo below has shown all of the unsuccessful PCBs that we have so far. We have been trying to implement different circuit designs to the project and make some adjustments according to the issues. The first image showing the initial solar charging circuit that we made. Because of the miscalculation of J's width, which caused the circuit got burnt out immediately as we connected it to the power supply. The second image was the updated version, but due to the incorrect wiring and soldering, the LCD display will not show up. And for the motor controller circuit, the components of the regulator were burnt out because we selected the wrong values for the capacitor. However, our group were able to identify the problem and proceed to make the better PCBs. So moving on to the administrative content. This is the milestone chart, which showing the current progress of our group. We have done all of the necessary research and also soldered the components on the PCBs. We also implemented the coding on the device, and the overall progress is 100%, and this device is working. The table below shows the outline of the expense for the project. The total balance is approximately $700, and this is the complete view of the major parts that we have used in our project. There are actually more components that we bought were not listed, and many of these were used for prototyping purpose. We also had to reorder couples of PCBs for the motor controller and the solar charging circuit, since they were burnt out during the time that we were testing. We pay everything by ourselves. Our functions well together as we trying to help each other out. Thank you for your listening. We are now open to taking any questions.